Oh, good, good.
Devote more time to my schoolwork.
Cool. Okay, so I'm going to call this week 12. I've been out for a couple weeks, and it sounds like Tim did a good job covering a few things for the exams. Where I left off was, I think we did a good job covering everything for Summary 3. Those are coming in nicely. Week 8 is Tidal, and I will dive into that just a little bit, and I know Tim covered it too. I changed this problem set to problem set number 2. So I don't think I had something labeled as 3. So 3 has become 2, and then I'll give you one final problem set as well by the end. Title continued, so we'll wrap that up. Let me see who's gone through exam 3. Temps allowed 5. Okay, so I think that's pretty much wrapped up.
I'll take it at once. I'm gonna take it.
Okay. Any questions on this one? I mean, I'm happy to go through it.
There were a couple.
I'm happy to go through it.
Because I have the old book, and I don't know if there's some information that's.
Oh, yeah. I'm just going to kind of roll through it here on different types of turbines, which are either accelerating or impulsing, and I think that's pretty well covered in the book. This as well. This is kind of looking at more or less the
One issue I had,
hydro resource.
the average power or energy output from the tidal barrage is, and then there's A through G. I know
Okay.
C is correct, approximately proportional to the square of the tidal range.
Mm-hmm.
I'm assuming there's a second answer then.
Okay.
I'm not sure which one of those it is.
Yeah. All right. Let's just take a look at that.
Yeah, there you go.
Yeah.
It's not C.
Oh, yeah, I remember putting this one together because I labeled them. Unfortunately, they're actually in order where A is A, B is B, C is C, etc. Okay, so proportional to the cube of the tidal range. Well, the tidal range is just going to be the height or the head, more or less. And that doesn't sound quite right. Proportional to tidal flow. Flow is going to be velocity, and if you cube velocity, you will have a time cubed in the denominator, so that seems likely. Approximately proportional to the square of the tidal range.
Yeah, that's verbatim out of the book. Right?
Okay, super. And then roughly proportional to the area of the water, the average power. Well, the area is not going to, the area is going to affect the energy, but not the power. So.
Right.
I don't know, let's just, let's try this one.
Then it says the average power or energy output.
Yeah.
So it'd be one or the other instead of both.
Yeah, that's a little misleading. I think we could just scratch that. I think what's implied there is the average power output or rate of energy output.
Okay.
Proportional to the tidal flow makes sense.
Yeah, let's just try it. I'm gonna throw that one down. Anything else stand out?
Yeah, I was a little bit confused about the Gulf Stream question. Because I always, growing up in Florida, was told that the Gulf Stream was a river.
Yeah.
It was just a river, but when I went through the book and started reading, it kind of felt like they were saying it was a tidal current, that's tidal stream. So I wasn't sure.
The current beneath the surface.
Yeah, that's a good one. Gulf Stream is driven by, among other things, differential solar heating of the Earth's atmospheres and ocean water. So we know that there's a couple things, at least from my understanding, that drive it. One is warmer water is going to rise. So wherever you've got warmer water is going to rise, and saltier, colder water is going to sink. So the way the way I understand it, so if you're at the equator and you've got a lot of heat coming in, that warm water is actually going to form kind of like, I might think of it like as a mushroom cloud, sort of growing out along the top. As water evaporates, the salts are left behind, so that water gets, hotter, saltier. It's got to go somewhere. The stuff that moves north, as it moves north, just gets colder. It's cold and salty, and then it dives. So that's kind of, my limited understanding from it. Differential heating of the Earth's atmospheres and oceans. So that's what's driving that thermohaline gradient, as it's called, as well as levels of salinity. As such, an example of. So tidal is going to be driven by gravity, not by solar. A river also driven by gravity and topology. Significant tidal variation created by the ocean floor. Probably not. So I'm going to go with A. We'll check to see if I'm right or not in a second. Any others?
Yeah. Okay, which statement correctly explains the physics of tides? I chose B, but I'm pretty sure it was D because I felt like both of them were correct. I'd like to know why B isn't correct.
Okay, all right. So physical tides. Tides are created by the pull of the moon on one side, and the centrifugal force of the Earth rotating on its axis on the other. As the Earth spins on an axis, it spins through these bulges to create tides. Yeah. So that's doesn't sound exactly wrong. Let's go to the next one. The tides are created by the gravitational pull of the moon and the sun. So that's more correct because it's the moon and the sun. So already that one sounds better. These forces act on the ocean's waters, creating bulges on the sides nearest the sun and moon as the Earth rotates, spins through the bulges. Yeah, because you could think of the if it were spinning through the bulges, the water would really be moving a lot faster. The water would really just be sitting there static while the Earth spun under it. So that last part's a little bit iffy. The tides are the result of the spin of the Earth on its axis and the orbit around the sun. The mutually interacting centrifugal forces create bulges on either side of the Earth through which the Earth rotates. No, not so much. Then the last one, D, tides are a result of gravitational interaction between the Earth's oceans with the moon and the sun as the Earth spins on its axis. Sure, okay. On the side of the Earth nearest the moon, the mass of the moon exerts gravitational towards the ocean, so the bulge outward. A second, so I can cover that guy. It's kind of wild the way this works out.
It's the centrifugal forces that I'm not.
Right.
I guess.
Yeah. Well, here's the simple example. So if I take my glasses here and I'm just kind of spinning them at a low rate, the radius is relatively small. But if I push it harder, then it spins out farther. So that's centrifugal force right there, sort of forcing it out. Then the tension is pulling it back. Let's just think about this a little bit. The oceans themselves are viscous, and it's kind of hard to think of something spinning outside of a gravity field, but in a sense, the whole Earth being its own gravity field. Obviously, if you put water in a bowl on a table, it's all going to go to the bottom. But in outer space, where the Earth is sitting, the water is all kind of pointed towards the middle. Now, there is a little bit of a bulge over all of the Earth. The Earth itself is not exactly solid, so the distance from pole to pole is a little less than around the equator. So the Earth itself bulges, but gosh, the effect on the water is just minimal. But here's where the magic of Newton's gravitational law comes in. Back in the day, we used to take a deep dive into the physics of this, but I've kind of backed off on it a little bit more recently. See if I can't get my bamboo working. Okay. So here's let's just say this could be the moon or the sun. Doesn't really matter which one it is. And here is the Earth. So Newton's law says the force of gravity equals the gravitational constant times m1 m2 over r squared. So this is r, the distance between the two, and this is what's classically known as an inverse square law. The farther away you are from something, the less gravity you feel, and this is why there's a little less gravity on Mount Everest than there is in Death Valley, for example. You're just further from the Earth's center of mass. What's a little bit strange, like if you went to the center of the Earth, you're like, oh, there's a lot of gravity down here. Well, there's no gravity at the center of the Earth because the rest of the mass is just all pulling you outward. So there's sort of a sweet spot, if you will, on Earth where you're sort of as close as you can get to as much Earth as possible, and so you're feeling the most gravity. It's just a few fractions of a percent, but that's where that r squared comes in. And the other kind of interesting. I'm going to show you one other kind of cool thing, but. So energy equals force times distance. We know that. Or if you're going to do some work, then the amount of work you do is how much force you push by how far it goes through it, and it's the same as E equals mgh. So in this case, the mg is providing the force. That's Newton's second law, F equals ma. And this is h is essentially acting as d. So that's how energy works in that case. So, but now we're talking force. So we can rewrite this equation as force equals energy over distance. So let's see if we did. Yeah, so that just immediately returns F equals mgh over d just becomes mg. So you can kind of see where that guy comes out. But in this case, yeah, here's how to think about it. So let's think about it this way. So the all of the gravitational energy of this sphere is contained within it. So as we move sort of further and further away from the sphere, all of the energy is contained within it, and so it is a function of like the volume. So if energy is a function of volume, the force becomes a function of area. So if we do it like this way, if we say energy is proportional to volume, force is proportional to area, simply because if you divide volume by length, you get area. So that's basically what's happening. That's that r squared, because the r squared represents the area of the sphere of interaction. So that's how I tend to think about it. And obviously, the bigger these two things are, so if we rewrite this as force of gravity equals g, mass of the sun times the mass of the Earth over r squared. Now here's the interesting part. If we just take a little chunk of water here and a little chunk of water here, the force, I'll just call this one F1, and I'll call this one F2. So obviously, since we could call this guy R1, and if we go all the way to the other side of the planet, we'll call that R2. So since R2 is greater than R1, F2 is less than F1 because of that inverse square. Because the denominator for the F2, for the far side, got bigger, so the force got smaller. So you can see right away, well, if the force is greater, hey, I'm getting pulled. And if the force is less, well, it's not pushing, it's just getting pulled less. Yeah, that's where it comes from. Yeah. Okay.
So with the axes effectively shifting, it would change the amounts the different areas of the world would have force applied.
Yeah, if
Did you say that's the reason why the North Atlantic current has stopped flowing?
it has?
It happened during the Little Ice Age because of fresh water.
Yeah. No, I think that's the whole. Yeah, I think that's the whole point. It's more. It's not so much a tidal thing. That's more the thermohaline effects.
Oh.
Yeah.
Yeah, that's one of the big concerns now. They're going pretty much this century because of all the water influx from Greenland. It's like a perfect. It's a really sensitive point because that's where the water likes to dive back down because it gets cold up there and then sinks and it comes back underneath the other higher coastal.
It's like two crashing rivers almost.
Exactly.
Yeah.
You introduce a whole bunch of really, really cold, non-saline water into that. It has a pain effect.
So the Marianas Trench would be affected too, because it's normally, would it be warmer down in the Marianas Trench, or?
No, I think it's pretty cold down there.
Okay.
Yeah.
Yeah. From above, from above, it ends up looking more or less like this, sort of an elliptical shape.
Yeah.
But of course, the Earth is spinning, so that this bulge sort of moves across the continents relative to where they are. Yeah. Okay. So I'll try
A
that.
few more?
Sure.
All right. This is in relation to tidal and ocean stream. It says, which of these factors has the greatest impact on power? Density of water, area swept by blade, or velocity?
Oh, yeah. Yeah. Right.
I think it's the velocity of water.
Yeah, it is. So the power equation. So if we look, so power equals. Well, let's see if I. So I'm ready to do this derivation here. Yeah. mv squared. Yeah, energy equals 1/2 mv squared. So that's whether we're talking about a chunk of air or a chunk of water. If we've got something that's moving towards a turbine blade that's spinning, that's the energy in this little mass, right? So it's mass. It's going with some velocity, and this whole thing has some area. And now, if we know that power equals energy divided by time, well, we know that this mass is moving, so we can say that power equals 1/2 m dot v squared. So that's the rate at which the mass is moving. So the faster the mass is moving, the more if it's not moving at all, you're not getting any power, right? So from here, we also know that mass equals density times volume. This is big V for volume. Now we know that the volume isn't changing. We also know that volume equals area times height. Well, we're just going to use this A as area of the mass moving through, and then we can also think of its little chunk moving through as H, so we can rewrite M as rho A H, and then we can write M dot. So the density is not changing. The water or the air or whatever is the same density. The area is not changing. That's just the area of the turbine. It's the height that's changing. It's that stuff that's moving. So that's just going to be, so H dot ends up just being V. It's the velocity. So then power becomes 1/2 rho A V cubed. So back to the question. So the density, that's linear. The area, that's linear. And the velocity is cubed. Yeah, that's cubed. So, so it's most sensitive to the velocity. Yeah.
The next issue is on propeller types and Newton's third law versus Newton's second law.
Yeah.
I guess I don't quite grasp how each one of these.
That is a weird problem. Okay, so let's just look at let's look at Newton's third law first of all. Well, so here's the first law is V dot equals 0. It just says that objects in motion stay in motion. The velocity is not going to change unless you kick it somehow. The second says F equals ma, so force equals mass times acceleration. And the third says that the sum of the forces equals 0. So if I'm pushing on the floor is pushing on me with the same. So this is, so there they are. So what would a third law turbine look like, and versus what would a second law turbine look like? So in the case of a second law turbine, you would have to have some kind of acceleration. In the case of the third law, you would sort of have a constant. I think the answer is reaction and impulse. Yeah. Okay. I think it's just reaction and impulse. I mean, as the name sort of implies. So the reaction turbine is an example. For every reaction, there's an equal and opposite. That pretty much is the third law, right there. And then the blank turbine is example second law, where you've got an impulse. So in the case of an impulse, you have acceleration, so something sort of, bouncing. And I do want to kind of look those up, so I'm not as familiar with those as I should be. Let's just take a quick peek out here. Impulse turbine, moving bucket, fixed nozzle. Yeah, so in this case, the water is sort of bouncing off of the thing. There's a famous example back in the gold rush days. There were these impulse turbines used to drive machinery, and they're very very effective because you kind of get a little extra bang for your buck there. with that guy, where the water's actually accelerating. It's like, bouncing off of this thing. And even if the gold miners didn't make any money, the guy building the turbines did, because they had to buy the turbine. And then in the reaction, the water is still changing direction, but and you still have a fixed. So you've got fixed nozzle, fixed stator. The rotating nozzle, though, itself is moving in the case of the reaction turbine. So there's kind of your equal and opposite. So the water's kind of going through this steady stream versus this sort of bouncing mechanism. That's the difference. Yeah, that's not my favorite question, but got to do something with it.
All right, I got a couple more.
Okay.
The power output of a turbo generator is. I think it might be all above.
Okay, equal to probably had the efficiency of the turbine, the flow rate, and the force of gravity. That looks a lot like B. Determined by how efficient it is, the height through it falls, minus the energy losses. Okay, volume of water, and the rate of acceleration. I think all three of those are the same exact thing, just one,
Yes.
just in different, in different words. Because that's your.
Well, I was pretty confident that when I selected C that it wasn't incorrect.
Yeah.
And typically that's turned out to be.
Yeah. So there's your gravity, there's your efficiency, there's your flow rate, and there's your head. So, and I think we did several problems earlier where I covered across and through variables. So in this case, H is the across variable. It's the amount of pressure. It's the same as voltage, and Q is the through variable. It's how quickly matter is moving through the thing. Yeah. So I'll go with that guy. What else?
Yeah, one more.
Yeah.
In hydro systems, the device most commonly used to convert the energy in moving water to electrical energy is.
Okay.
Typically, I would guess it's steam turbine.
Oh, no. In the steam turbine, you've actually got. You actually have hot water turning into steam. So that would be more for a coal-fired power plant.
Primitive.
Yeah, just hydro, and hydro is shorthand for hydroelectric. Yeah. In the Stirling engine, also you've got a heat cycle. A propeller is something that's moving a boat, so that's not it. Turbo generator, well, that's a pretty good guess because that's what you're trying to do is generate electricity. And the alternator, gosh, what's that? That's just typically think of that in an automobile. And it is converting rotational energy into electrical energy, but the turbo generator.
Energy recycler.
Cool.
Yeah, recycler, converter, shifter, something. Yeah.
I'm not a mechanics man. Never owned a vehicle.
Really?
No.
Wow, you must be a millennial. Never owned a vehicle.
Yeah.
That's
Just
saying something.
Too expensive for my blood.
Well, finish
But
attempt.
Time will come. I'm gonna get a Tesla.
Yes, you are. We're all going to drive Teslas next year.
My old man was out on the West Coast for about a month, and he ran into an old friend, Matthew Fox, the actor. He was in Party of Five. He was the doctor in Lost.
Wait, Matt, not Michael Fox, but Matthew Fox. Okay.
Fox. Yeah,
Okay.
best known from that TV show Lost.
Okay.
Apparently, he's pretty good buddies with Elon Musk, and he owns 3 Teslas.
Nice.
Yeah. He was
Nice.
Talking all about it.
Yeah.
He's kind of on the in when it comes to. He thinks it's going to be like 3 to 5 years before the whole in-home battery for multiple days of storage thing actually becomes
Yeah. Yeah.
voluntarily available.
Yeah. Yeah. No, it's. I think it's going to come a lot faster than we think. We're working with another group up in northern part of the state, Vision, and they've got this flow cell battery, so it's, it's a battery about the size of this room, zinc phosphate, and apparently a lot of times, like when Hollywood's going out to shoot somewhere, like, out in the wild, they need it quiet on the set, so they don't want a bunch of generators running out there, so they use this battery. Yeah, well, put them on a truck, let it roll.
That's well, yeah, 'cause,
Yeah.
I mean, that really, for the whole living off-grid thing, I mean, 3 to 5 days.
Yeah.
Power is,
Those are some of the predictions, look at some of the Musk videos out there, and he says, in 10, 20 years, we'll be able to make more energy than we consume. Because remember that there's that 10,000 to 1 ratio. I mean, we only use about 1/10,000th of the amount of solar that hits us. And so as solar becomes efficient, as we get more batteries, we'll see it.
It'll speak volumes to the big corporations too, the giant warehouses with empty rooftops, just lining them with solar.
Oh, yeah.
Once corporations dish money into that product,
It accelerates for sure.
It's going to be cheaper and more widely available to the private
Yeah.
people.
I was just flying back yesterday, and there were a couple guys, one's like, die-hard Grizz, and kind of an older guy, been around the block a couple times, had a veteran's cap on of some type. Like, they shipped me off to Saudi and stuck me in a container for 3 months, and I just poured concrete, because they're just going bonkers with solar over there, apparently, too. Yeah, because they've got their hands on the tap. They know what's coming down. Okay, so I think we got that one right. Let's see if we got any of them wrong that we tried.
Yeah, I didn't look at any of the.
Ties a result. That's correct.
Yeah, the rest of these are pretty straightforward.
Oh, I clicked the wrong one. I think.
Oh,
Yeah, I just clicked the wrong one. We knew what the answer was, but I just absentmindedly clicked the wrong one.
Cool.
Oh, and I must have clicked the wrong one too. That's not what I said, but somehow I clicked one that I was not intending to. Triple generator. So what's that guy? This one is confusing. Average power energy output from a tidal barrage. Tidal range, proportional tidal flow.
Would be the cube of the tidal.
Let's just see what the answer is. C and D are correct. Roughly proportional
to
the area.
water trapped behind the tidal water.
So that would speak to energy, wouldn't it? That's not a well worded question, because I said, it's the area is more how much energy is a function of area. Okay.
Good, it's not just me.
Good.
I don't know, would it be
So C-
volume instead of area?
Well, and then what's C? Portion of the square of the tidal range. Oh, I see. So, square of the tidal range. I'll have to come back to that one. I don't have that one off the top of my head. I'll have to come back to that. All right, let's take a quick break.